All right, welcome back, everybody. This is a special 7th period edition of the video. This is section 4.1. So let's talk about the second semester of Calc and what we cover. We again covered 3 chapters in the second semester, just like we covered 3 chapters in the first semester. We covered chapter 4, 5, and then 6. In terms of the tests, like first semester, there was a test for chapter 1, a test for chapter 2, a test for chapter 3. That's not the case in the second semester. We have a first half of chapter 4 test. We have a second half of chapter 4 test. We have a chapter 5 test. And we have a chapter 6 test. There's actually 4 tests within the second semester. 2 in the third 9 weeks, 2 in the fourth 9 weeks. Now, just as a reminder, you guys are done May 12th. Right? That's your last day of school, so I need to get everything done by that date.
You're gonna miss my birthday.
When's your birthday?
17th.
I'll be here.
I'll
You come in.
We'll celebrate.
I expect to see a Zoom call.
Zoom call. Yeah, me and son.
I expect to itch my leg.
So we have to get everything done by that date. Now, it's going to be a little bit different than in years past for me because this is the first time I'm teaching calc not on a lunch period. Now, why does that affect things? Well, especially during the second semester, when we have testing days, this class gets shortened every testing day. I've never taught it off of a lunch period before. Like last year, calc was 4th period. It never got shortened because it was on a lunch period, even for any testing day, because those are turned into late start days. So our class is going to get shortened quite a bit for several days when we start into April. So I might have to move a little bit quicker than I usually do, but I think we'll be fine. But again, 4 tests. We'll do chapters 4, chapter 5, and chapter 6. Chapter 4, the beginning part of chapter 4 is all about what's called optimization. Optimization. Now, when we're looking to optimize something, that means that word optimize really just means finding the best of, right? To optimize something means to find the best way of doing something, right? Some of the most important applications of differential calculus are called optimization problems, in which we are required to find the optimal or best way of doing something. Here are examples that we will solve in this chapter. We actually do an example just like this first bullet points on one of our tests. What's the shape of a can that minimizes manufacturing costs? I give you manufacturing costs set up as an equation. You have to minimize manufacturing costs to figure out the dimensions of a cylinder, basically. What is the maximum acceleration of a space shuttle? What is the radius of a contracted windpipe that expels air most rapidly during cough? At what angle should blood vessels branch so as to minimize the energy expended by the heart in pumping blood? Now, we don't go that far in depth, but that's really the applications that you could get into. Basically, what we're saying here is that if you can create an equation to model a situation, I can optimize that equation to give you the best way to make that happen. Okay? I could optimize that equation to give you the best way to make that happen. Like, I can, given certain parameters, I can maximize like fuel efficiency. I can maximize profits. I can minimize costs. This kind of goes back to something that we did in Algebra 2 is called linear programming, where I gave you a certain set of parameters, and then there was an objective function that you tried to maximize or minimize, find the biggest or smallest amount. And we did that just graphically, where it was very geometric, and we had to find intersection points and run it through a certain equation, and that was the maximum or minimum value of that function, and that's what the optimization was. We didn't really call it optimization, but that's really what we were doing. Now, that was more on the algebraic side. What we're going to be looking at this is, okay, how do we do that same thing with calculus? Okay. Now, to optimize something, to find the best way of doing something, requires us to be able to find the maximum or minimum values of a function. Maximum and minimum values of a function. And that's all our first lesson here. That's section 4.1, finding maximum and minimum values of a function. Take, for example, that diagram that you see on the right side of the screen. I see a function with closed intervals. I see a function with closed intervals where it's got a topping out and then a bottoming out. Right? We see it topping out at 3, 5, and then we see it bottoming out at 6, 2. We can say definitively, as long as this is truly on a closed interval, there's no arrows on the other sides, we can say definitively that the highest this function gets is 5. The highest it gets is 5. The lowest this function gets is 2. We can also describe where that's happening. I can say at the x value of 3, this function maximizes to 5. At the x value of 6, this function minimizes to 2. So that's what we're talking about with this idea of maximum or minimum value. Now, there are differences between an absolute maximum and minimum value or a local maximum and minimum value. Let's first start to define our absolutes. Here's our definition of absolute, mathematical definition of absolute maximum and absolute minimum. It says that the absolute maximum value of a function, and understand that I'm talking about the y value, the true output is the maximum or minimum. That's why I said, the minimum value was 2. It occurred at 6, but the minimum value was 2. The smallest that function got, the lowest that function got was 2, the output. The absolute maximum value of f, of a function f, on its domain D, that's what it's saying there, the maximum value of the function f on the domain D is f of c, so some location c. You run the output value, you get f of c. F of c greater than or equal to f of x everywhere within the domain. That's our definition of absolute maximum. The value of the function f on its domain such that f of c is greater than or equal to f of x. The output for at c is bigger than the output at anywhere else in that function. And I can contrast that with absolute minimum. The value of the function f on the domain D such that f of c, the output at c, is smaller than, less than or equal to all other x's when I run them. That's our mathematical definition of an absolute maximum and minimum value. It's the biggest possible or smallest possible value of that function. We're talking in absolutes. Biggest or smallest possible. Now, you know what throws things off? If I had done this, if I continue that function onward, and it's no longer on a closed interval, it's no longer just in an interval, if I continue that function up and down, now are those 2 points absolutes? Is that dot at 3, 5 the biggest? No, because there are other y values that are bigger. Right? So how do we talk about that? Well, that's no longer an absolute maximum or minimum value. It's still got a special name. It's what's called a local maximum or minimum value. Now, the definition is very similar. The only thing that changes is this word here, near. And that's kind of like that's where the definition starts to get a little fuzzy. How do you define near? How close is close? A local maximum is just basically a value of a function that's bigger than the others around it, close to it, near it. A local minimum would be the value of the function that's less than all others around that point, near that point, close to that point. That's what a local maximum or minimum value is. Excuse me. Just put some Reagan today.
Yeah, Maddie.
Oh, Maddie. Oh yeah, that's right. They're on a cruise.
They're on a cruise?
Yeah.
For what?
Caribbean.
It's not West Virginia. It's not over.
I want to go on a
They
cruise.
didn't know where they were going.
So you
Yeah.
just got back from LA.
Yeah, really.
I did not just get back from LA. I just got off Christmas break. So,
I just got back to
They literally know where I'm going.
We're building schools
No.
down there for the
All
children.
right, so let's take a look here at this diagram.
Lower Akron.
I'm going to look at the right side and then I'm going to look at the left side. So the local minimum here. This basically says that this point is the smallest around. Smallest near that location. Is it the smallest total? No, that's the smallest total. So that's why we would call that a local minimum and an absolute minimum. Here, why don't I call that why don't I call that an absolute? Yeah, because it's going up over here, isn't it? Right? Here's the deal about local and absolute maximums and minimum values. If it's an end point on a closed interval, so let's assume that this is a closed interval. Okay? Let's assume that that's a closed interval. Let's assume that those are closed dots. An end point can be an absolute maximum or minimum, but it cannot be a local maximum or minimum. Let me repeat that. An end point on a closed interval can be an absolute maximum or minimum, but it cannot be a local maximum or minimum. Here's why. Think about it like this. You know, I can build up to this on the right side. Think about it like limits. The right side limit of this thing exists, right? Does the left side limit of that dot exist? No, because there's nothing over there. The function is not defined on the left side. So think about it with our definition of limits. The limit does not exist from the other side. So therefore, near has no meaning on the other side because it's not defined on the other side. So that's why it's not a local maximum, but I can consider it the absolute maximum because it is the biggest total overall. Okay. Here, this coordinate over here would be nothing. You wouldn't consider that a local or absolute minimum or maximum value because it's not the biggest or smallest around, or it's not the biggest or smallest total, and it's an endpoint, so it's not a local. Okay. So now what I'd like to do is kind of explore some functions, like cosine. Let's think about the maximum or minimum values of cosine. And let's talk about them as absolutes or locals and see what we get. Now, I've got our diagram here. We could create this. But I think you guys know cosine well enough. Here's what cosine looks like. What is the local and absolute maximum value? Local and absolute maximum.
1.
1, right? Both the local and absolute maximum would equal 1. Why? Because that's the biggest y value that I could get. Does it matter that it's occurring multiple times? Nope. Because they are still local and absolute maximums. Now, you may be thinking, well, how do I define where they occur? Okay, it all depends on how the problem is asked. Like this one, it just talks about, exploring them. So if I asked you where they were occurring, you would say at x equals. Now, in this case, it's going to keep cycling through, right? It's going to happen at 0 plus 2 pi n, where n is an integer. Because it's going to happen at 0, at 2 pi, at 4 pi, at 6 pi, at negative 2 pi, at negative 4 pi, at negative 6 pi. You don't always have to add, unless I specifically ask for it, you don't need the x value. Technically, the y value is enough. The local and absolute minimums would therefore be what? Negative 1. And that would occur at pi plus 2 pi n. Because again, that's going to happen cycling through every iteration of 2 pi. Pi, 3 pi, 5 pi, 7 pi, and going to the negative. Negative pi, negative 3 pi, negative 5 pi. Okay, so that's something that's cyclic, the ones that might happen over and over again. Let's think about the basic quadratic, the parent quadratic x squared. Oh yeah, sorry. So great, so good. I'm trying to think of a joke. How many feet are in the yard?
3.
Nah, it depends on how many people are in the yard.
Oh, good one.
Hey, son, what's a duck's favorite thing to eat?
I feel like you never hear these jokes.
All right. What can I tell about the parent x squared? It's a parabola. What can I tell about its absolute or local maximums or minimums?
I want one also.
Can I want? No.
What do we see down there at the bottom?
Red.
A minimum value, right?
Yeah.
A minimum value. Is that a local? Is that an absolute? It's both. Local and absolute minimum value is 0. And again, we could say it's occurring when x is 0. Yes?
Is it absolute because it's the lowest
Nothing
point on the
lower.
graph?
Right. It will never turn back downward if it's just x squared. Does this have a maximum value? You might be tempted to say infinity, but remember, to be a maximum value, it needs to be an output of the function. Infinity is not really an output, it's like an idea, right? It's just it's going there, right? So there is no absolute maximum or even local max, whatever it may be. Okay? Questions about that? Okay, let's take a look at x cubed. Will this function have an absolute maximum or minimum? No, because it's going to dive down forever on the left side. You know, the book gets a little lazy with arrows. But we know that it's going to go downward and upward forever. So there are no absolutes. Is there a local? Is there a local?
Yeah.
If it was anywhere, where would it be? 0. At 0, right? Well, let's kind of investigate it at 0. What if I just put blinders on and did not look at the right side of the graph? You would be tempted to say at 0, 0 is a what? A maximum, right? What if I put blinders on the left side?
Oh, that's a minimum.
Could it be a local maximum or minimum? No, not at the same time. Think about it like the limit rule. It's got to match both left and right side. Okay? It can't be a maximum on one side and a minimum on the other. Because if you say, oh, this is a minimum value because all points around it are bigger than it. Well, that's not true. Because on the other side, I've got points below it. I'm good, thank you. I actually had to read this for yesterday.
Wow. So you have slightly stale readers.
No, I did not. Same thing on this side. I cannot say that. I would be tempted to say that this would be a maximum value. By definition, this y value is bigger than anyone around it. Well, that's not true because it doesn't match the right side. So we would say there are no absolute or local max or minimum for x cubed. So it all kind of depends on the function. Okay. So let's take a look at something really weird. I've got some quartic function on a closed interval from -1 to 4. I've got this quartic function on a closed interval. We are going to define the local minimums, the local maximums, the absolute minimums, and the absolute maximums. Where are the local minimums? Zero and give me the y value.
-27.
Right. So 0 and -27 are the y values. They occur at 0 and 3, but the minimums are 0 and -27. What is the absolute minimum? -27. That's not a coordinate. I'm not saying 0, -27. I'm just listing them. What is the local maximum? Watch out. An endpoint can't be a local. Give me the y value. 5. The local maximum is 5. It occurs at 1, but it is 5. What is the absolute maximum? What's the absolute maximum? 37.
I thought it could be an endpoint.
A local can't be an endpoint.
Okay.
An absolute can be an endpoint. And that's the key difference here. An endpoint of a closed interval function can be an absolute, but not a local, because there's nothing coming from the other side, so they can't define near it. All right. Let's talk about this thing called the extreme value theorem. This is going to lead us into a couple other theorems, but this first one basically says that if f is a continuous closed function, that's actually going to be the premise to a couple theorems. If the function is closed and continuous, if f is closed and continuous, then it has an absolute maximum and minimum value somewhere along that line. As long as it is closed and continuous, then it has an absolute maximum or minimum value along that line. They can occur more than one spot. They can be the endpoints, because again, absolutes can be endpoints. I'm not saying locals, I'm saying absolutes. So like here, I have this closed continuous function. I have this point C that is our absolute maximum. And again, watch out here. They occur at C and D, but they would be the y values. Our absolute maximum is occurring at C, and absolute minimum is occurring at D. Look here. An absolute maximum is occurring at C. An absolute minimum is D, which is also B, one of the endpoints. It can occur at more than one spot. Say like cosine. I have two absolute maximum values right there. I have an absolute minimum here. The weirdest case of this is if I had points A here and B here that were level, and it's a flat line, a constant function, that basically is saying that A and B are both our absolute maximum and minimum values. Okay? A and B are both C, and A and B are both D. They all have the same y values. So therefore, they're the biggest and smallest that they could possibly get. So if it's a constant function like that, those points are actually the absolute maximums and absolute minimums. Okay, but that's the weirdest case. Let's talk about when it's not continuous, because the premise of this function, of this theorem, says that as long as f is continuous on a closed interval. So let's look at when it's not continuous, when it has a discontinuity, and when it's not closed. Take a look and see. Take a look at this one, the first one. You see I have a discontinuity?
Mm-hmm.
If you have a discontinuity, then you can't have an absolute or local maximum there. Well, I guess we have to be very careful about it. Because you might be tempted to say, well, the local maximum is 3. But is the y value of 3 defined in the function? No. So it can't be the maximum. Okay? I get it. It's around there. Yeah. Now, if I change this slightly and make the closed dot there and the open dot there, do I have a local maximum now? Yes, because that coordinate of 3, that coordinate of 3 is the highest around. And is 3 defined on that function? Yeah. So that is a local maximum now, and in this case, our absolute maximum. Is there an absolute maximum in this second one? No, because it's going to go up forever. Is there an absolute minimum on this? No, because it's an open dot on the low point. Is it local either? No, because it's an endpoint. Okay, so you've got to be careful with those. Now, this is extremely important. This is the big one here. It's called Fermats Theorem. Fermat. Pierre Fermat. That's his name. Pierre Fermat. It says that if f has a local maximum or minimum value at c, and if f prime, we're bringing in derivatives now. If f prime of c exists, then f prime of c is 0. That's a very, very, very big statement right there. It says that if a local maximum or minimum exists, then the derivative is 0. Think about it. I've got different points here where I've got local maximums and minimums. What's happening every high or low point to the tangent line? It's going to be a horizontal tangent line where the slope is 0. Okay? So Fermat's theorem says that if you have a local maximum or minimum, at that location, the derivative is going to be 0. Now, you have to be very careful because the converse of this is not necessarily true. It's not false. It's just not necessarily true. Okay? If the derivative equals 0, it doesn't necessarily mean that it's a local maximum or minimum. Like take, for example, the cubic function. What's the derivative right here? 0. Does it have a local minimum or maximum there? No. This is representing a counterexample to the converse. This is where a derivative equals 0, but there is no local maximum or minimum there. Okay? So the converse of Fermat's theorem is not true. Just like this, take a look at the absolute value function. Do you see a local minimum? Yes. What is the derivative at that point? It does not exist. It's undefined. We looked at this as an example in chapter 3. The derivative does not exist because it is a corner point, right? You may be thinking, well, wait a sec. You just said if there was a local minimum, the derivative equals 0. But there was one caveat to that. I made an exception. If the derivative exists, then it equals 0. So basically what I'm saying is, if you have a local maximum or minimum, either the derivative does not exist or it equals 0. Those are the two implications there. If you have a local maximum or minimum, then either the derivative does not exist or the derivative equals 0 at that location. And I believe that's where I wanted to stop for tomorrow. Perfect. Get to the exact same spot as earlier today. Warning! You have to be careful.
You have just been calculated.
What?
It's like a whole new Spanish book. And now if I try to put it in
Did you end the recording?
Oh, now I did. Now I did. What'd you say?
Something.
I mean appropriate.